Hey folks, welcome back. Today we're going to be talking about thermochemistry, specifically Hess's Law. This is the last one we have to worry about for thermochemistry. So let's relate thermochemistry to something else that we understand. Let's say that you're going to climb a mountain. This happens to be Mount Washington in New Hampshire. Doesn't matter. Let's say that it takes you 10,000 calories a day to climb the mountain, but it takes 2 days. So let's just look at these first two things. It takes 10,000 calories a day and it takes you 2 days to climb the mountain. How many calories do you exert to get to the top of the mountain? Well, obviously that would take 20,000 calories. You just multiplied by 2. Okay, that's pretty easy. And, 20,000 calories. How about if there were 3 of you? So it took 3 of you, 2 days each, to climb the mountain. So how many calories would that be total? Well, obviously that would be 20,000 per person, but I now have 3 people, so that would be 60,000 calories. Now what happens if you slid down the mountain? Well, in theory, you get all of those calories back. Alright, so you get negative 60,000 calories. And in fact, if you thought about it, if you have a sled to ride down this mountain, you could actually do that. Well, as I said, this is Mount Washington in New Hampshire. It doesn't take 2 days to climb the mountain. It only takes 4 hours. But the concept is the same. All right. They do have a railroad that goes all the way up. And when they built the railroad back in the 1800s, the guys had to climb up the mountain, and they used these little wooden things they called devil shingles to come down the mountain. So they would ride the mountain down. So yes, they would climb up the mountain, and they'd carry that thing with them. And then at the end of the day, after they'd finished their work, they'd hop on the thing, and they'd come shooting back down to the middle, shooting back down to the bottom. And in the middle, you'll notice they have these little things here, and these are the cogs that the train pushes up on. And so they just come on down, and they do have a brake, although it doesn't work too terribly well. So they'd come flying down this mountain at about 60 miles an hour or more. And as a result, some of them died flying off the thing. So they stopped this practice in the early 1900s. Anyway, bottom line is we understand that it takes, that if you've got 2 people or 3 people, you're multiplying the effect of 1 person. Well, that's what Swiss chemist Hess decided when he was talking about chemical reactions. And he said, if you take a series of chemical reactions and you add them together, the enthalpy change for the net reaction will be the sum of the enthalpy changes for each of the steps. Okay, so how in the world do we apply that? What does that mean? Well, let's say that what you want to know, what you don't know, but what you want to know, is you want to know the enthalpy change for this reaction. You want to know the delta H for this reaction. And the question is, what is the enthalpy change for that reaction? Well, you don't know. But you do happen to know this information. You happen to know that if I start with nitrogen gas and I add oxygen gas, I get 2 nitrogen monoxide molecules. And when I do that, I have to put, this is positive, so this is endothermic. So I have to put in that much energy to make it happen. But then, if I take those 2 nitrogen monoxide particles that I just made, and I add more oxygen to it, I get 2 nitrogen dioxide molecules, which is what I wanted over here, and that is exothermic. And so we get back some energy when that happens. So the concept is we want to be able to, Hess's law says, we can add these 2 things together. So if I have N2 plus O2, and it gives me 2NO, and my enthalpy change there is 181 kilojoules, and I have 2NO plus O2, and that gives me 2NO2, and that is a negative 113, that's exothermic kilojoules. I should be able to add these together, and what I get is N2 plus O2 plus 2NO plus O2. You'll notice what I just did was I just added everything that was on the left of these arrows. So I just added all of these things together, and I'm going to add all of these things together on the right-hand side of the arrow, which is 2NO plus 2NO2. Well, and then I'm going to add these 2 numbers together. Right? When I add those 2 numbers together, I get 68, and it's positive kilojoules. All right, so I look at that and I say, well, this equation down here that I just got does not look anything like that equation up there. But wait a minute. I notice some things about it. I notice that I've got two NOs over here on the left-hand side of the equation, and I've got two NOs on the right-hand side of the equation. So since they're on both sides of the equation, I can delete them. They can go away. So they're just going to disappear. All right. I also notice here I've got an O2, and here I've got an O2. So couldn't I put those together? Because an O2 plus an O2 would give me 2 O2, which would leave me with N2 plus 2 O2s, give me 2 NO2s. And again, my delta H for this equation is positive 68 kilojoules. Wow, it actually works. So that's the concept that we're going to be applying. Now, to be able to do this, of course, you want to have the right number of N2s and O2s and NOs and all that to make this equation up here. So we're going to show you how to do that. So the application of Hess's law, which is what we just did, is useful when a given reaction can be written as the sum of two or more reactions for which we know the enthalpy change. So we do have a couple of rules. We can multiply coefficients. So if the coefficients are multiplied by a factor, the enthalpy change is also multiplied by the same factor, or potentially divided. If reaction is reversed, then the sign of the delta H reverses also. It's kind of like climbing up the mountain versus coming back down. When you do the reverse, you get all of that energy back. So all you're doing is switching the sign of the enthalpy change. So let's look at an example. Rule number 1 talks about if coefficients are multiplied by the same factor, the enthalpy change is multiplied by that same factor. So let's look at this equation here. N2 plus O2 gives 2NO. Now if I double everything, you'll notice 2N2, 2O2, 4NO. If I double all of this, what I have to do is take this and multiply it by 2. Right? If I take that and multiply it by 2, I get 362 kilojoules. Now if I take that same equation that I start with, and instead I divide everything by 2, so I only have half an N2, half an O2, and only one NO, then I have to take this number and I have to divide it by 2. So instead of having 181, I've only got 90.5 kilojoules. Now, of course, these are both positive. Okay? That should make sense. That's pretty easy. That's kind of like we did when we were climbing the mountain. Okay? But this one is like what happens when we come back down the mountain, if the reaction is reversed. So instead of climbing up, we're going down. The sign of the delta H changes also. So in other words, if a reaction releases heat in one direction, it absorbs heat, exactly the same amount of heat, in the reverse direction. So here I've got my carbon plus my water on the left, and here I've got my carbon plus water on the right. And I've got carbon monoxide and hydrogen gas on the right, and over here I've got it on the left. So all I did was, instead of going up the mountain, I went down the mountain. So I went from a positive 113 kilojoules to a negative 113 kilojoules. It just went from endothermic to being exothermic. That's all that happened. All right, so let's go ahead and see if we can apply this to a couple of things. So I'll do one for you, and then you can actually see how the whole thing works. Now, the way that I do this is I'm trying to calculate this down here. All right, so this is what I look at. And I'm trying to calculate my delta H, my enthalpy change, for this reaction. So I look, for example, for sulfur in my equation, in my two equations up here. Now, I notice that the only place that I see sulfur is right there. Now, it's important that it's the only place I see sulfur because that really helps me balance this. Remember, balancing equations, we looked for things that were singles before they were doubles. But I notice, for example, that there are two S's up here, but there's only one S. I only want one S. Only want one sulfur. So I have to take this equation and I'm going to divide it by 2. So let me rewrite this equation down here. So I have one S and I have 3 halves or 1.5 oxygens. and it's going to produce only one SO3 because I'm dividing by 2, and my delta H for this reaction is going to be half of 790. Okay, and half of 790 is negative 395 kilojoules. All right, let's look at my other one. I've messed with this reaction. I've already done that. O2. What do we do with O2? Well, O2 is here and it's here, and that makes O2s very hard to balance. So we're going to leave it alone. If we possibly can, we're going to leave it alone and not balance it, and hope that it works out. And in reality, that's exactly what we do. So let's look for the third thing that we have here, which is SO2, which is a gas. And the only place that I find SO2 as a gas is right here. And I'll notice that there are 2 of them up here, but I only want 1. So I'm going to have to divide by 2. But I also notice that my SO2 over here is a reactant. It's on the left-hand side of the arrow, and I want it on the right-hand side of the arrow. So I'm going to have to reverse the sign here to make it, it's currently exothermic, I want to make it endothermic. All right, so I'm going to take this reaction, I'm going to turn it around. So the first thing I'm going to do is turn it around, and when I do that, I also have to divide by 2. So I'm going to get SO3 over here, and then it's going to produce SO2 and only half an O2. So what I did was I flipped the reaction, and I divided by 2. So now my delta H for this reaction, what I have to do is instead of negative 96, I have to make it positive, and I have to divide it by 2. When I divide it by 2, that's 98 kilojoules. All right, so let's add these 2 reactions together. Well, I have an S, and I have 3 halves O2, and I have SO3. And that's all on the left-hand side of the arrows. Now on the right-hand side of the arrows, I have SO3, and I have SO2, and I have half an O2. Now I also have to add these 2 numbers together, and so my delta H is going to be negative 297. Did I do that math right? Kilojoules of energy. Hopefully I did. Okay, so now, but can I make this equation down here, still doesn't look like this equation up here. Oh, but I noticed there's some things that are duplicated. For example, I have SO3 on the left and I have SO3 on the right, so they can go away. And I notice I have 3 halves O2 on the left and I have half an O2 on the right. So if I combine like terms and I subtract half an O2 from this side, I have to subtract it from that side, and that gives me just an O2. So I have S plus O2 giving me SO2, and my delta H for this reaction is going to be negative 297 kilojoules. So I'm done. That's exactly what I wanted to do. All right. What I'd like you to do, if you can, is see if you can plan this one out. Pause the video. Remember, when you see what... Oh, let me make a comment. Once I've changed an equation and I've written it down here, I don't have to write it again. I've done it once. And so once you've changed an equation, don't change it again. Right? So that's one of the concepts. And the other concept that I would do is if you have something in multiple equations, like here I have oxygen in multiple places, don't mess with it. Just leave it alone. Let it work itself out. Okay? See if you can do this one. Pause the video. See if it can work out for you. Okay. What do we start with? Well, we're looking to try and make this. So I look at the TiO2, and I find it, and the place that I find it is there. Right? Now, I only have 1 in my final, what I'm looking for, what I'm trying to calculate, and I've only got 1 in the problem. So that's great. The problem is it's on the wrong side. I have to put it on the other side, which means I have to change my delta H and make it negative. So let me rewrite that equation as TiO2 plus CCl4 gives me TiCl4 plus CO2. And I have to change the sign so it's negative 155 kilojoules. All right, now what about my next thing? Well, CCl4, notice that CCl4 is right there. I've already changed CCl4. Notice CCl4 is now on the reactant side. So I've already taken care of that. I don't need to mess with that again. So I leave it alone. So I look for Mg, and I notice that Mg is over here on the left. The only place it is right here. And Mg is over here, and it's on the left, but I've got two of them. So I have to take this equation here, and I'm going to have to multiply it by 2. So let me go and rewrite that as TiCl4 plus 2Mg. I have to multiply everything by 2 in the equation, and that produces Ti, and it produces 2MgCl2. And so I have to multiply my negative 239 by 2, and that gives me a negative 478 kilojoules. All right, so now I have to add these things together. Well, this is going to be messy, right? So I have TiO2 plus CCl4 plus TiCl4 plus 2Mg. And that's going to give me TiCl4 plus CO2 plus Ti, wow, this is a long one, plus 2MgCl2. Now I also have to add up these two numbers here, and that's going to be negative 633 kilojoules. So that tells me the energy for this equation should be negative 633 kilojoules. But again, this doesn't look like what my target equation is until I notice that I have certain things that are duplicated. For example, I have TiCl4 here, and I have TiCl4 here, so I can cross them out. And now it looks like I do have the equation that I wanted. I do have TiO2 plus CCl4 plus 2Mg. Now that looks like the left, right? And over here on the right I've got CO2 plus Ti plus 2MgCl2. And that looks like the one on the right. Well, I mean, these things are backwards, but who cares? They're both on the same side of the equation. I'm producing them. So my answer here is going to be negative 633 kilojoules. So this thing works. Cool. All right, let's do another one. Again, pause the video. See if you can do this one on your own first. All right, hopefully you did and you tried to do it on your own. I noticed that this one, I've got a CS2 here. It's the only place it exists, and that's where I'm trying to get. So this reaction is fine, exactly as written. Now let's see, I've got H2O, and the only place I see H2O is up here, and it's on the wrong side, and I have to have two of them, so I have to take this, I have to change the sign, and I have to multiply it by 2. So in other words, I'm going to take this reaction, I'm going to reverse it. So I'm going to leave the first equation as it is, CS2 plus 3O2 gives me CO2 plus 2SO2. And my delta H there is negative 1075. And this other one I'm going to take down and I have to multiply it by 2 and reverse the sign, so I'm going to write it backwards. So 2H2O plus 2SO2 gives me 2H2S plus 3 halves times 2, that's going to be 3O2. And so I have to take that, multiply it by 2, multiply by delta H by 2, so the 563 times 2 is 1,126, and I have to reverse the sign so I make it positive. Okay, if I add those two together, I get a positive 51 kilojoules as my delta H. Let's see if this works. Well, I'm not going to rewrite the whole thing, but look here, I've got 3 O2s, and I got 3 O2s, and they cancel, right? And I've got 2 SO2s on the left, and I've got 2 SO2s on the right, so they cancel. So what am I left with? I'm left with CS2 plus 2H2O gives me CO2 plus 2H2S. And look at that. It works out. That's the equation I'm looking for. My delta H is positive 51 kilojoules. All right, this is the last one. A little bit more complicated. Go ahead and pause the video. See if you can do it. And use all the same rules. Okay, and we'll see what we come up with. Please pause the video. Okay, so let's look at what we have. I look for S, and the only place that I see sulfur is right here. It's on the proper side of the equation, but there's only one of them, so I have to take this, and I'm going to have to multiply this by 2. I look for OF2. let's see, the only place that I find OF2 is right here. It's a reactant, but I need 2 of them. So I have to take this one, and I'm going to have to multiply that by 2. And let's see, I look for SO2. And, well, you know, I see SO2 here, and I see SO2 here. So I'm going to let it work itself out. I'm going to ignore it. So I'm going to look for SF4. And SF4 is over here. So it's simply, there's one of them on both sides, but it's on the wrong side. It's on the wrong side, so I'm going to change its sign, and I'm going to flip that equation around. So let me rewrite these 3 equations. I have to take this first one and multiply by 2. So it's going to be 2OF2 plus 2H2O gives me 2O2 plus 4HF. And my delta H there, I have to multiply by 2. So 277 times 2 is going to be 554, and it's going to be negative 554 kilojoules. And let's see, this one, I'm reversing the sign. So I'm going to write it backwards. So it's SO2 plus 4HF. Don't have to multiply by anything, so it's SF4 plus 2H2Os. And my delta H here is simply reversed. So instead of being negative 828, it's positive 828 kilojoules. And my last one down here, I have to multiply by 2, so I get 2S, plus 4O2 gives me 2SO2. And here my delta H has to be multiplied by 2. So that's going to be negative 594 kilojoules. All right, well, let's take those 2 negative ones, add them up. That's 1148. And that's negative, and the positive one is 828. And if I add them together, I get a 0, I get a 2, I get 320. So my answer here is negative 320 kilojoules. Let's see if this works out. Well, what do we have over here? We have, I remember the SO2s were in multiple places. So we do have, I've got SO2s over here, and I've got SO2s over here, but I've got 2 over here and only 1 over there, so I can get rid of this 1 and make that a 1. So I've got 1 SO2 over there. And let's see, can we cancel anything else? We have the 4 HFs over here, so they can go away. And we have SF4s, H2O. Oh, we've got 2 H2Os over here. We've got 2 H2Os on the left, so they can disappear. And we have 2 S's. We've got 4 O2s. I did something wrong. 2 S's. That's 2 O2s. I knew something was wrong. When I multiplied this S by 2, that by 2, that by 2, that should be 2 O2s. These 2 O2s cancel those 2 O2s. You've got to be real careful. Obviously, I wasn't careful enough. Okay, so I'm left with 2 OF2s plus 2 S's give me SF4s plus only 1 SO2. And that is, in fact, what I have up here for my equation. The order is slightly different, but that's okay, because the left-hand side matches what it's supposed to, and the right-hand side matches what it's supposed to. So I'm done. So my delta H for this equation is negative 320 kilojoules. All right, folks, that is it for Hess's Law. Please do the worksheet. You need some practice on this. If you have questions, please let us know in class, and then you'll be ready to do the labs and take the test. Have a great day. We'll see you in class. Bye-bye.